Hello and welcome back to Functional Analysis. And many thanks to all my great supporters on Steady and PayPal. You really give me the motivation to put all this work in making these videos. So thanks a lot. In Functional Analysis, we've already reached part 12, and today we will talk about continuity. To be more precise, we will talk about continuity for metric spaces. For this, we just need two metric spaces, so one set X with a metric dx and a set Y with a metric dy. And now we consider a map from X to Y. And now such a map is called continuous if the pre-images of open sets are always open. More concretely, we would write the pre-image of a set B in Y. So now this usually denotes the pre-image of B, but I want to make that really clear, so I want to use brackets here. I think that's helpful because every time you see the brackets, you know this is not the inverse map, it's the pre-image. Okay, now we say this set is open in X for any open set B in Y. Okay, so this is the formal definition, and now I can give you a picture to remember it. So we have our metric space X on the left hand side, on the right hand side we have our metric space Y, and in between we have the map F. Now for any open set B in Y, we find the corresponding pre-image on the left hand side. Now the property continuous means that if you start with an open set here, you also get an open set here. By thinking about boundary points, this means that if you don't have any boundary points in this set, you also don't have any boundary points in this set. In fact, you can also read that from left to right by looking here at an input. And you change the input a little bit by small distance. You know this is always possible because you are in an open set. And then you know on the right hand side, the output is also only changed inside this open set. Of course, this notion seems a little bit abstract. Therefore, now we look at something we call sequentially continuous. As the name tells you, this has something to do with sequences. In some sense, I can repeat what I told you before. We choose any output on the left hand side, and let's call it x tilde. And also let's look at any sequence xn that converges to x tilde. And then it should hold that the new sequence f of xn is convergent to f of x tilde. In other words, every convergent sequence on the left hand side gets translated into a convergent sequence on the right hand side. You might already guess, for us it might be easier to work with the notion sequentially continuous because we just have to deal with sequences there. Now the good thing is that for metric spaces, both terms mean indeed the same thing. In other words, one can prove that they are in fact equivalent. For that reason, we will simply use the word continuous, but often mean this characterization with sequences. However, I wanted to show you both definitions because if you don't work in metric spaces, but in general topological spaces, in general, both notions are not equivalent. Okay, so I write down the fact and then we can look at examples. Okay, maybe you already know a lot of examples, so let's look at some simple ones. The first one would be choosing x dx as the discrete metric space. So where X is any non-empty set. Now on the right hand side, it does not matter which metric space we choose, so let's say it's any metric space. Now let's look at the map F from X to Y, and then we can conclude that this one has to be continuous. This is simply the case because all subsets in a discrete metric space are open sets. This means that checking the definition of continuity is immediately given here. So keep that in mind whenever you see a discrete metric space on the left hand side. Now another general example like this would be to consider a constant function. For this we can choose x and y as general metric spaces and then fix a y0 in y. In this case then we know that the map F that sends all the x to y0 is always continuous. Indeed, this is what you see immediately by looking at the definition of sequentially continuous. Simply by looking at this part where you know this is always fulfilled. The left hand side is always y0, the right hand side is always y0, so we stay at the limit point for all n. Okay, with this in mind, let's go to two other examples I find very important. For the first example, I want to look at a normed space. Of course, we always have the induced metric space in mind. And y should be just r with the standard metric given by the absolute value. And now the map I want to consider is f given by x to r, where an element x is sent to the norm of x. And now our claim is that is always continuous. Okay, so for this let's write down a proof, so we check that the map is indeed sequentially continuous. Hence, let xn be a sequence in x with limit point x tilde. And then we look what happens when we apply the map f. Of course, f of xn is just by definition the norm of xn. Now we have to bring in the limit point, because that's the only thing we know about the sequence. It has a limit. So what I do is subtract the limit and add it again, so we add a 0 here inside the norm. We do that because then we can apply the triangle inequality. So I write xn minus x tilde in the norm plus the norm of x tilde. And then we know the first part is just the distance between xn and x tilde, and the second part is just f of x tilde. By assumption, we now know that the distance between xn and x tilde goes to 0 when n goes to infinity. Hence, doing the limit on both sides, we get that the limit of f of xn is less or equal than f of x tilde. Okay, so you see that's already half of the work we have to do. So now let's go from the other side and show the other inequality. Therefore, we start with f of x tilde, which is just the norm of x tilde. Doing a similar thing than before, we just put in xn. So subtracting and adding again. Of course, now redoing the triangle inequality gives us x tilde minus xn in the norm plus the norm of xn. Which is a similar result as before, because we have x tilde xn in the metric plus f of xn. Now I don't have to tell you, applying the limit on both sides, we get the inequality the other way around. And with that, our proof is finished, because we have shown that the sequence f of xn converges with respect to the metric in R to f of x tilde. So we conclude the norm is always a continuous map. Okay, so you might guess, with the next example, we go to an inner product space. So let's choose X as an inner product space, where we already know it's also a metric space. And Y should be just the complex numbers with the standard metric given by the absolute value. Now, since an inner product has two entries, I want to fix the first one with a given x0. Now the map we consider is f defined from x to y, so C, and the vector x is sent to the inner product x0 with x. And the claim is again, this map is a continuous one. As before, I really want to show you a proof of this statement. Of course, the procedure should be the same as before. We consider any point x tilde and a sequence that is convergent to this point. However, now maybe we can do it in one step when considering the absolute value of f of xn minus f of x tilde. In other words, this is the inner product x0 with xn and x0 with x tilde. Using the linearity, we can put that together, so we have just one inner product. Now, every time you see something like that, you know you can apply Cauchy-Schwarz. This means that we have the inequality I will abbreviate with CS. And it tells us we have the norm of x0 times the norm of xn minus x tilde. Since this last part is the distance between xn and x tilde, we know this goes to 0 when n goes to infinity. Moreover, the whole right hand side goes to 0 when n goes to infinity. In conclusion, also the left hand side goes to 0 because it was non-negative from the beginning. And then we know the sequence fxn converges to f of x tilde. Okay, so we have shown that the inner product is a continuous map in the second argument. And by symmetry or using the same argument as here, we can also show that it is a continuous map in the first argument. This is important to know for a lot of proofs we will do in future, and I show you one now. Indeed, this is the cliffhanger from the last video, so we have an inner product space and a subset U. And then U perp, the orthogonal complement of U, is always a closed subset. Proving this is not hard at all, because now we know all the things we need. Now please recall part 4 of the series, where I described closed sets with the help of sequences. So what we have to do is choose a sequence in the set itself, where we know it's convergent, but first just in the space X. Now when we can show that the limit X tilde is also in U perp, then we know U perp is closed. Okay, so now we just have to use the definition of U perp, which means that inner product of Xn with U is always 0 no matter which U we choose. Since this equation holds for all n, we can look at the limit and know this is also 0. And now we know we can pull in the limit here because this is just the continuity of the map G we stated before. In other words, we just have X tilde with U is equal to 0. And since this holds for all U in U, you see this is just the definition of U perp. X tilde is also in U perp. And this is exactly what we wanted to show. The orthogonal complement is always a closed set. And you have seen this immediately comes from the continuity of the inner product. Okay, I think that's good enough for today. Thank you very much for listening, and please check out the PDFs if you want. Of course, I hope I see you next time when we go further into the topic of functional analysis. So have a nice day and see you then. Bye!